We continue with the topic of solving a system of linear equations and inequalities. But today we're going to continue talking about tools to solve a 2x2 system or a 3x3 system. So we're going to discuss a second way of doing this, which is using determinants and the Kramer's rule. So this is a more systematic way of doing this. It could be somewhat tedious, right? So we will just go over a case of a 2x2 system and a 3x3 system. This takes longer, right? So this is longer to do. Okay, so the objectives are evaluate the determinant of a 2x2 system. So once we learn how to calculate this, we're gonna use the values of the determinants to find the solutions of a 2x2 system and a 3x3 system. So let's go first with what is a determinant, right? It's basically it's a square matrix, right? So we're gonna see that we're gonna have two cases, a 2x2 and a 3x3, right? So this makes them square, right? So it's not a 2x4 or a 3x4, right? Or 2x3, right? So it's none of those. Okay. So a square matrix, in this case we have a 2x2, A, B, C, D. So the way we calculate the determinant is basically multiplying A times D minus B times C, right? That's basically the flow, the way you do it, right? So you go like this, minus, and multiply this way. Okay. So let's see some examples. For example, it says evaluate the following determinants. So we have a square matrix with the elements 2, -4, 5, and 9. So the determinant is going to be 2 times 9 minus, and here we have to be careful, minus 4 times 5. Right? So 18 plus 20, 38. Okay, you see here we have 38. Okay, so why don't you pause the video and then try this one. After coming from the pause, so you have minus 3 times minus 5 minus 0 times 8. That will be 15. Okay, so doing 2x2s is not that difficult, right? But now we can use this to actually find the solution of a system. So if we have a 2x2 system like this one, where A, B, C, D, S, and T are constant values, right? So the variables are going to be the X and Y, right? So these are basically the two variables. Okay, so the solution of this system is going to be the value for X is going to be the determinant of X. Okay, so what is the determinant of X? Notice that here we have the values of S and T, which is the right hand side values, and here we have B and D, right? So this is Y. That's the way you set it up. Down here we have the determinant of the system. You can see these are the coefficients for both the X and Y. Okay, so please take your time to analyze this. And here you can see the determinant of y is basically, again, the matrix. You can see the S and T values are placed in the y column. And here we have the coefficients for x. And here we have the determinant of the system. Okay, so you have to calculate the determinant of x, the determinant of y, and the determinant of the system. And then you can find x as the determinant of x over the determinant, and y, determinant of y over the determinant. Okay, you might find this more difficult, right, because it's tedious, it's the first time, but this is much simpler than solving a 2x2 system by elimination, right? If you just plug in these values and they just work, right? So here we have, it says use Kramer's rule to solve the following system. So that's the key. Kramer's rule, you say, oh, that means that x is going to be the determinant of x over the determinant, and y is going to be the determinant of y over the determinant, right? So you find these three matrices. So the determinant is going to be 2, 4, minus 5, minus 2. And then the determinant of x is pretty much the same. The only thing is that you take the right-hand side values and place them in the x column, and the other two stay the same. And the determinant of y will be 2 and minus 5, and in the y you place the right-hand side values. This doesn't go there. Okay, you solve this, you find the values of these three determinants, and then you plug in the values here and here, and that will be your x and y. So the determinant is going to be 2 times minus 2 minus 4 times minus 5. Determinant of x is going to be minus 2 times minus 2 minus 4 times 13. And the determinant of y is going to be 2 times 13 minus 2 minus 2 times minus 5. Okay, just basically multiplying or finding the solution of these matrices. Okay, so I'll give you some time to, or pause the video, find those values, okay, and then I'll show the solution. So you can pause now. Okay, so let me just get rid of this and then just basically show the three determinant values. Right here we have the determinant of x. Remember replacing the right-hand side values here. And these are the values: 16 minus 48. Determinant of y, same deal here. And here we have the value of 16. Right, so we have that x is the determinant of x over d, y determinant of y over d. So basically just plug in those values. Okay, so if you notice, it doesn't matter the type of equation that we have. or system of equations that we have here, all we have to do is just plug in the values in that order, you know. Here it's just basically replacing coefficients. Okay, you can see these are the right-hand side values here, these two, right? So if my equation changes to a 15, let's say, all I have to do is just change this to 15. And then go here and change here this to 15. Get my new two values, and voila, right? I will get X and Y with a new set of numbers, right? I don't have to do all the elimination stuff. Okay, once you get your values for X and Y, you plug them in the original equation and you check both equations. Now, with a 3x3 system, it's more complicated, right? Because we have to find several determinants. So here we have, by definition, the determinant of a 3x3 system. Okay, so what you do is that you take the first element here, that's A1, okay, and you get this matrix, right? That's the one that you see here. Okay, basically eliminating the row and the column that intersects with A11. Then you jump to minus A12, which is this one here. So what you do, you eliminate this row and this column, and you are left with these four values, right? Those are the ones that go here. And guess what? Then you go with the third one, which is this one right here. And what you do, you eliminate row and column. So that means that you are left with this matrix. And that's the one that goes here. Okay? And then you find the determinant of this 2x2 matrix, right? So it's just more tedious. But again, the advantage is that you take this 3x3 system, and once you find the X and the Y and the Z, in this case, it will be just easy to find the solution, right? Because again, it's easier to compute, right? You don't have to eliminate, you don't have to substitute, and you don't have to do any of that stuff that we did before, right? Just finding the values of the determinant. It's just a little more, it's longer, more complicated. Okay, so let's set up this system and solve it using Kramer's rule, right? So here we have a 3x3 system. Okay. So again, we're gonna find the determinant of the system, the determinant in X, and the determinant in Y. Okay, you're gonna see that here we're gonna set up, perhaps they set it up the problem a little different, which is also valid. So here we have a 3x3 system. So again, we are going to reduce. I'm going to show what the author did, which is also valid. So we have, this could be somewhat a little bit confusing, hopefully not. But here we have this 2 that comes from this index. So the values that we're going to use are this 4 that goes here. Now, instead of using for these 3, instead of using this one, which is also valid, but instead the author went another route. I'm using the author notes just in case you see something different in my MATLAB. They actually use this one right here. This three is the one that goes here. How do I know that? Because let me erase. Because the values that you use, 3, 0, -1, and 2 are the ones left when you eliminate this row and this column, which you can also do that. You will get the same value. And then here they just went down with the 1. Okay, that's the one that you see here. Eliminating this row and this column, you are left with 3, 0, 7, and -4. Those are the ones that you see here, right? Which is basically the same. Okay. When I say the same, it will be another option will be to do go here to doing 2, and then I'm left with 7, -4, -1, and 2, -3. Using this one, then it will be 3, -4, 1, and 2, and then using the 0, which actually I would have done this, is easier calculation, 0, 3, 7, 1, and -1. You can also do that, which is the first thing that we did. Okay, so 2 different ways of getting an answer. Okay, so you calculate that. I'm gonna leave that for you to calculate. Here you have the actual calculation, right? So 7 times 2 minus 1 times -4. That's what you see here. Here, this calculation again is because of this determinant, and this calculation because of this one. And then you reduce and you get a value of -10. So see if you get that -10. If you don't, please let me know. Then you have dx, right? So again, 4 comes from here, -3 comes from here, 9 comes from here. Okay, you calculate the matrices, the determinant, okay. So again, I'm gonna leave that calculation to you so you can practice. -50, and then dy, you do the same. Okay, reducing the matrix from one side to the other, and then calculating each determinant, right? So again, it's systematic, but it's pretty much all the same. You get the value. Okay, so now once you have, and then you do the same for DC, right? So see if you can set up the values and do that calculation. Now, once you have all 4 values, it's a matter of substituting to get X, Y, and Z. Okay. Okay, so notice that we have values for D as -10, for dx as -50, dy 20, and dc -10. And this is important because now we have, we have a solution. This system has a solution. Okay, but if you guys remember, there are cases where we have infinite number of solutions for a dependent system, or are infinite or null for an inconsistent system. And the nice thing about the Kramer's rule is that we can figure these things beforehand. Okay, so let me just give you the solution for DC. These are the checks. Okay, so here we have some rules. We have the case where we have an inconsistent system where it's null or empty solutions. So it says here that if the determinant is 0, right, and at least one of the determinants, the x, the y, or the z, is different than 0, then we have something that is inconsistent. Okay, so if we have, let's say, for example, for an inconsistent system or no solution, something like this: d is equal to 0, the x is equal to 0, the y is equal to 5, the z is equal to 0. So that will be inconsistent. Now, if all of them, d is equal to dx, is equal to dy, is equal to dz, and all of them are equal to 0, then this is a dependent system. Okay, so when you get a 3x3 system, you calculate the 4 values, and then if all of them are 0, it's dependent. If one of them it has a number and the rest is 0, it's inconsistent. Okay, but the determinant can never be 0, right? That's not good. Why? Because when you use a Kramer's rule, let me go back. Right, so when you use Kramer's rule here, if the determinant is 0, then you will be dividing by 0, right? So you can't, so here this cannot be 0. Okay. Let me go forward now. So here, the first thing that we should do is calculate the determinant of the system. If that is not 0, then we have something going on. If it's 0, then we have problems. Then we have to find what kind of condition do we have, inconsistent or dependent. Okay, so if there are any questions, please make sure that you send me an email. And then on the next section, we're going to talk about linear inequalities.